Math Physics Medicine, MPM, and Viscoplastopology, VPT, differences, similarity, and evolution from geometric topology to viscoplastic energy. Part 1, number 1457, VPT Sharp 020, December 5, 2025 05,30. Gerald C. EclaireMD Foundation. Category, Medical Research Methodology. Preface. In the early morning at 05,30 a.m. on December 5, 2025, I woke up from my sleep, and suddenly saw a pattern that can combine my two medical research methodologies into one. Therefore, I decided to write it down in this theoretical descriptive paper to document my research, work, learning, and methodology expansion. Quantitative and automation. Almost everything can be described quantitatively if we look deeply enough. Music, for example, is built on do-re-mi, which can be expressed as 1 2 3. With further and somewhat deeper mathematical effort, I believe we can discover which combinations produce the most heart-touching and long-lasting emotional memory in the human brain. As someone trained in science and engineering, who later self-studied medicine, I naturally see the world through quantitative structures and pattern recognition. I see the world in terms of measurable structure, numerical patterns, system behavior, and cause-effect relationships. This is why I understand how digital systems replaced analog systems. Every analog domain eventually became digital because signals can be quantified, noise can be filtered, information can be reconstructed, and patterns can be recognized. I also understand how AI is already replacing part of human labor today. AI replaces routine tasks, repeats existing patterns faster, scales decision-making, lowers cost, and expands system capability. I also know that AI will replace even more in the future, including part of medical practice. AI will increasingly take over roles that depend on pattern repetition, data sorting, large-scale comparison, risk estimation, early detection, and trend analysis. These are precisely the tasks that VMT and TDA enhance as well. However, human uniqueness will remain in intuition, creativity, emotion, empathy, and ethics. Everything else will shift gradually toward automation. Viscoplasticity in medicine. In December of 2020, my MIT PhD advisor, Professor Norman Jones, wrote an email to me from the UK, suggesting that I should use the viscoplastic method for my medical research work. He noticed that my papers up to that point relied on various methods from simpler forms of both mathematics and physics, such as statics and linear states in multiple domains of time, space, and frequency, which I named the Math Physics Medicine, MPM. His reason was clear: biomedical behaviors are time-dependent, meaning all biomarkers of diseases and their influential lifestyle or medication factors are changing with time. I then went to my study room, where I have collected around 20,000 books and my handwritten lecture notes from 18 years of university studies. I studied 8 academic fields at 6 different universities from 1964 through 1982. Back then, there were no computers or digital devices, so everything learned was kept through handwritten materials. After searching, I realized that Professor Jones had taught me dynamic plasticity, without the viscosity element. The concept of viscosity, which means time-dependent or changes with time, or internal fluid friction, was discovered by Isaac Newton in 1687 and documented in his work, Philosophiae Naturalis Principia Mathematica. Professor Jones was one of the early research scientists who brought viscosity into solid mechanics in the early 1960s. When he taught at Brown University, his research work on viscoplastic behaviors of various structural geometries, such as columns, plates, shells, rings, etc., helped Boeing design the jumbo jet in the 1980 era. However, during my study years at MIT and Cambridge, Massachusetts, 1972 through 1976, his research on viscoplasticity remained in the research domain, not in classroom teaching curriculum. Therefore, in early 2020, almost 6 decades after his pioneering research work in engineering at Brown, MIT, and the University of Liverpool, I finally went online to search for related educational materials to self-study the subject of viscoplasticity. Starting from April of 2021, after 3 months of self-study on websites, I began using Excel on my PC to simulate the Viscoplastic Medicine Theory, VMT, for my medical research work. By the end of 2021, after many months of hand computing data, I decided to develop software code to install into my iPhone device. Starting in mid-2021, I developed computer software to run my VMT, numerical computations, and the processing time was reduced from hours to 2 seconds. Unfortunately, I did not spend time automating the graphic generation by software. Instead, I still use Excel to draw all necessary graphic diagrams. Despite the tedious nature of this graphic generation task, it helped me develop deeper insights into my research findings. Through this long and tedious journey, I have finally learned far more, and developed an instinct regarding data insights from handling data points, datasets, lines, curves, areas, volumes, mathematical geometry, and physical energy. Research work has no shortcuts without sweat, there is no harvest. I have gained a great deal from this difficult path. During the more than 700 viscoplastic medical research papers I have written over the past 5 years, from April of 2021 through December of 2025, Topology in Medicine, after my hemorrhagic stroke in the pons area, which controls breathing, heartbeat, and food swallowing basic living functions, I suffered some memory loss, including both short-term and long-term memories. Strangely, the pons area has nothing to do with memory function, but after the stroke, I was readmitted to Stanford Hospital. Due to multiple seizures, doctors suspected that my memory loss could have resulted from seizures as a complication of my stroke. Nevertheless, I focused on my self-developed method and exercise process during the golden window of stroke recovery, the initial 99 days after the stroke. Different from mobility paralysis and speech difficulties, there are very few research literatures available for both memory loss and cognition impairment. On my hospital discharge day of June 28, 2025, my memory loss level was about 40%, which means I could only remember 60% of the items I saw 10 minutes earlier. By September 30, 2025, my memory loss rate improved to 2%, meaning I could remember 98% of the items I saw 10 minutes ago. Another noticeable evidence came from my research paper productivity. During the last 156 days, I produced 150 long research papers, around 2,000 words each, and 33 short articles, 500 to 900 words each. On average, this is about 1.17 papers per day. Prior to my stroke, I generated about 0.67 papers per day, or 1 paper every 1.5 days. This represents a 75% productivity improvement. More importantly, I noticed that the quality of my research work has improved, my view angle is wider, and my research depth is deeper. For example, I realized that all of my medical research work is related to mortality diseases, resulting from chronic metabolic disorders, while Professor Jones spent his lifetime studying catastrophic phenomena such as rupture, permanent damage, or collapse of structures. In other words, both of our research fields belong to the category of outliers, or extreme cases in the statistics domain, which are often ignored or smoothed out by averages. We do not study mass data averages, like most traditional biomedical research using statistical methods. My research work deals with the outlier subject of death, but most of traditional medical research relies on statistical averages, or regression models from mass population data. I also realized that the healthcare industry is driven primarily by economic interests, such as revenue and profits, where science is only the tool rather than the goal. The medical field is also strongly influenced by the food processing industry, the insurance industry, and particularly the pharmaceutical industry. In contrast, academic fields in natural science and engineering focus more on science itself, not economics. In October of 2025, I suddenly remembered topology, a subject I learned 58 years ago from the father of Samuel C. King, who was a professor at MIT in 1976 when he won the Nobel Prize in Physics. In November of 2025, I also suddenly remembered stochastic methods. I learned 48 years ago at UC Berkeley. I had never used either subject in my professional research work, nor even remembered them after completing those courses 5 to 6 decades ago. Through neuroplasticity, my repaired or newborn neurons reconnected with my old neurons, like opening old drawers and finding forgotten files that had not been used, or read for 5 to 6 decades. Within the past 3 months, I have applied topology to my medical research and produced around 50 papers, using it, not on medical imaging subjects using their geometric data, but on theoretical pathophysiology data through their geometric shape, changes and data point connectivity. I produced only 1 paper using stochastic methods, and then stopped due to my own personal bias against statistical methods, because they are not accurate enough for real and serious scientific work. The difference: my medical research method based on physical energy, the Viscoplastic Medicine Theory, VMT, calculates the interaction energy between a single output strain and its associated multiple influential input stressors. This energy can be obtained from the enclosed area of the multiple stress-strain curves. My other medical research method is mathematical topology, based on geometric shapes, and the amount of shape size changes and data point connectivities, using area for 2-dimensional cases and volume for n-dimensional cases. This is the Topological Data Analysis, TDA, approach. On the surface, these two research methods look totally different. One is based on physics and engineering, and the other is based on theoretical and applied mathematics. However, they do have clear differences between them. One deals with energy, and the other deals with geometry. The similarity: if we examine them more deeply, both of these two medical research methods, VMT and TDA, deal with quantitative data, including both input data and multiple output data across a longitudinal time scale. If we temporarily ignore the fact that engineering and biology are branches of applied physics, and physics is a branch of applied mathematics. Then we can say that, theoretically, both VMT and TDA belong to the same category of data science. More specifically, they both belong to one distinguished branch of pattern recognition, which happens to be one of the cores of the artificial intelligence, AI, domain. However, today's AI is more about pattern repetition than true pattern recognition, because current AI still lacks intuition, the so-called sixth sense, and creativity, creating something from nothing, not to mention human emotional feelings and passion toward others. In other words, today's AI tools can imitate human language of care and love, but they do not have a heart, meaning the human brain portions controlling neuron functions of emotions, passion, care, and love. Continuation. Up to here, this article has approached around 1,900 words, an artificial limit I set for the length of my own papers, less than 2,000 words, but I do not want to delete or reduce any words or sentences that try to express my true deep insights, feelings, or acquired and stored knowledge in my brain. Therefore, I will continue my writing in a second part of this long research paper, which will be dedicated to a detailed, step-by-step description of each research method. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.